Hello guys, today we want to solve one sample final exam. So this exam is for December 12 of 2017. So exam is 3 hours, and at first we want to have a quick look on the questions, and then we start to solve them. So in the first question we have to find a Laplace transform of one function. So it's the first part of the question. In the second part, we have to find a Laplace inverse of one function. And in the part B, so we have to use Laplace transform to solve the following differential equation. And in part C, we have to solve HT, where HT is convolution of the functions ft and gt. So on ft and gt, they are defined here. So it's question number 1. It's about Laplace transform, chapter 4. In question number 2, which has 20 marks, so we have to consider this function and we have to find Fourier cosine series. Then we have to sketch the function, sketch the Fourier series on the interval of -12 to 12. Then in part B, we have to see the Fourier series converge to what? At x equal to 0, x equal to 4, and x equal to -12. And in part C, we have to sketch Fourier sine series without finding the series on separate graph, still on interval from -12 to 12. Question number 3, so it has 20 marks. So in this question, we have to find Fourier series of following function. It's a piecewise function. So then in part B, we have to show that the given set of function is orthogonal on the indicated interval. Then we have to find normal function and construct one orthonormal set. Question number 4, so it has 20 marks, so we have to solve boundary value problem. In fact, here we have one Laplace equation and boundary conditions are given. So we have to solve this problem. And in question number 5, we have to solve one wave equation. So again, boundary conditions are given. Initial conditions are given, so we have to solve them for problems number 4 and 5. So you do not have to go through all 3 possible cases for separation constant. So in fact, for lambda, we should not consider lambda equal to 0 or negative. We have to just assume that lambda has a positive number. So at the end, we have the formula sheet. So we have table of Laplace transform. All the formulas are given. We have convolution. We have Fourier series on the range of -b to p. Here we have Fourier sine, Fourier cosine, trigonometric identities. We have solution of linear ordinary differential equations for problems number 4 and 5. And we have definition of orthogonal set. So let's start with solving the first problem. In question number 1, part A, we have to find Laplace transform of e to the power of -t times cosine 2t. In order to find Laplace transform of this function, I write it in this form. So it's Laplace transform of t times e to the power of -t times cosine 2t. In order to solve this problem, we need to know Laplace transform of cosine 2t. We need to know first translation theorem, and then we have to know derivatives of transform. So we have all of these 3 theorem in the Laplace table. So in fact, we have Laplace transform of cosine kt in this table. We have first translation theorem here, and we have derivatives of Laplace transform as well. So let's apply these theorems to solve first question. So in fact, Laplace transform of t times e to the power of minus t cosine 2t, it's equal to minus 1 to power of 1 d over ds times Laplace transform of e to the power of minus t cosine 2t. In fact, I used property of derivative of transform to end up with this equation to minus 1 d over ds Laplace transform of e to the power of minus t cosine 2t. So I can use first translation theorem. I can say that it's equal to Laplace transform of cosine 2t. But I have to replace s by s minus minus 1. So it's going to be s plus 1. So it's equal to minus d over ds Laplace transform of cosine 2t, I know it's equal to s over s squared plus 4, but I have to replace s by s plus 1, so it's going to be s plus 1 divided by s plus 1 squared plus 4. Now we have to just take derivative of this function. So if you take derivative of this function, we have 1 minus here, so denominator squared. Derivative of numerator times denominator, so it's going to be s plus 1 squared plus 4 minus derivative of denominator times numerator, so minus 2 times s plus 1 times s plus 1. So you don't need to simplify this function, but in case you want to simplify it, you're going to end up with s plus 1 squared plus 4 to the power of 2, and in numerator we have 1 minus here, 4 minus s plus 1 squared. So we could solve part A of question number 1. In part, still we are in part A, so now we have to find Laplace inverse of e to the power of minus 3s divided by s cubed times s minus 1. So in order to find this Laplace inverse, I write it in this form. So it's Laplace inverse of e to the power of minus 3s times 1 divided by s to the power of 3 times s minus 1. In order to find Laplace inverse of this function, we need second translation theorem and we need partial fraction decomposition. So if you look at formula sheet, so here you can see second it's a first translation theorem, and you know partial fraction decomposition. As a result, we can easily solve it. At first, I use partial fraction decomposition to find components of 1 over s to the power of 3 times s minus 1. So it's equal to a over s plus b over s squared plus c over s cubed plus d over s minus 1. So if I add these four fractions, we have s cubed times s minus 1 in denominator In numerator, so we have a times s squared plus times s minus 1 plus b times s times s minus 1 plus c times s minus 1 plus d times s to the power of 3. I can rewrite this fraction in this form, so it's equal to s to the power of 3 times s minus 1 in denominator. So if I factor s cubed, so we're gonna have a plus d s cubed. If I factor s to the power of 2, we're gonna have minus a plus b s to the power of 2. If I factor s, so we're gonna have minus b plus c times s, and we have 1c left. So right hand side of equation should be equal to left hand side of equation. Denominator are the same. As a result, numerator should be the same. So it means that a plus, at first we have to look at coefficient of s to the power of 3. So in right hand side we have a plus d. In left hand side we have just 1. So as a result, coefficient of s to the power of 3 is equal to 0. Then we have to look at coefficient of s to the power of 2. So we have minus a plus b in right hand side of equation. In left hand side of equation, coefficient of s to the power of 2 is equal to 0. Then coefficient of s in left hand side of equation is minus b plus c. In right hand side, in left hand side is equal to 0. And coefficient of s to the power of 0 in right hand side of equation, it's minus c, and in left hand side of equation it's equal to 1. So if you solve these three equations, you can end up with a, b, c, and d. So in this case, a would be equal to minus 1, b it's equal to minus 1, c it's equal to minus 1, and d is equal to 1. As a result, I can write this function in this form. So it's equal to Laplace inverse of e to the power of minus 3s times a over s. A is minus 1, so it's minus 1 over s. B is minus 1, so it's minus 1 over s squared. C is minus 1, so it's minus 1 over s cubed. And d is equal to 1 plus 1 over s minus 1. Now you can easily find this Laplace inverse using second translation theorem. I write it here. So it means that Laplace inverse of e to the power of minus 3s times 1 over s cubed times s minus 1, it's equal to unit step function ut minus 3 times, so Laplace inverse of 1 over s, so it's 1, so we have minus 1. Laplace inverse of 1 over s squared is t. They are all in the table of Laplace transform, so as a result it's minus t minus 3. Laplace transform of Laplace inverse of 1 over s cubed is 1/2 t squared, so as a result it's minus t minus 3 to the power of 2 over 2. And Laplace transform of 1 over s minus 1 is e to the power of t. So as a result, it's plus e to the power of t minus 3. So we could find Laplace inverse of given function. We are done with part A of question number 1. Let's go through the part B. In part B, we want to solve one ordinary differential equation using Laplace transform. So we have y double prime plus y is equal to root 2 sine 2, but here 1t is missing, so it's sine root 2 times t. So where y prime at 0 is equal to 0 and y0 is equal to 10. In order to solve it, we have to use the Laplace transform of derivatives. So you have this formula in the formula sheet. So in fact, here you can see Laplace transform of derivatives. So in fact, Laplace transform of fn, so is equal to Sn, s to the power of n fs minus s to the power of n minus 1 f0, and so on. So let's apply it in our problem. So we have to take Laplace from right and left hand side of equation. So we have Laplace transform of y double prime plus Laplace transform of y. It's equal to Laplace transform of root 2 sine root 2t. As a result, so Laplace transform of y double prime is equal to s squared y minus s at y equal to 0 minus y prime at t equal to 0 plus Laplace transform of y, it's y, and it's equal to Laplace transform of root 2 times sine root 2t, it's equal to 2 over s squared plus 2. You have this Laplace transform in the formula sheet as well. So we have y prime at 0 is equal to 0. So this guy is equal to 0, and y at 0 is equal to 10. So as a result, if I factor y, so we're gonna have s squared plus sorry s squared plus 1 minus 10 times s, it's equal to 2 over s squared plus 2. I want to find ys. So if I want to find ys, y is equal to 2 over s squared plus 2 plus 10s, and it's all divided by s squared plus 1. I can simplify it. If I simplify it, so ys, it's equal to, so I just simplify and expand it. It's gonna be 10s to the power of 3 plus 20 times s plus 2 divided by s to the power of 2 plus 1 times s to the power of 2 plus 2. So we want to find Laplace inverse of this function. In order to find it, we have to use partial fraction decomposition. So in denominator, we have s squared plus 1, s squared plus 2. As a result, here I have s squared plus 1. And here we have s squared plus 2. In denominator, we have as plus b. And here we have cs plus d. We have to find a, b, c, and d. So I just expand right hand side of equation, so it's equal to s to the power of 2 plus 1 times s to the power of 2 plus 2. If I expand it and then I factor, so we're gonna end up with this guy. So it's a plus c times s to the power of 3 plus b plus d s to the power of 2 plus 2a plus c times s plus 2b plus d. Now we look at coefficients of s to the power of 3, s to the power of 2, s and s to the power of 0 in right hand side of equation, in left hand side of equation. So if you look at coefficient of s to the power of 3, so you have a plus c in right hand side of equation, and in left hand side of equation you have 10. If you look at coefficient of s to the power of 2, in right hand side of equation you have b plus d, in left hand side of equation you have 0. If you look at coefficient of s, in right hand side we have 2a plus c, in left hand side we have 20, and s to the power of 0, in right hand side we have 2b plus d, and in left hand side we have 2. Now we have to solve these four equations to find a, b, c, and d. So if you solve it, you can see that a is equal to 10, b is equal to 2, c is equal to 0, and d is equal to minus 2. So it means that ys it's equal to a is 10, so it's going to be 10s plus 2 divided by s to the power of 2 plus 1, and plus c is equal to 0, d is minus 2 divided by s to the power of 2 plus 2. So in this question you're going to find yt. Yt is Laplace inverse of ys. Let's find Laplace inverse of ys. So in fact yt is equal to Laplace inverse of ys. Ys we already found it. It's equal to 10s divided by s squared plus 1 plus 2 over s squared plus 1 minus 2 divided by s squared plus 2. If you find Laplace inverse of this function, you're going to end up with 10 cosine t plus 2 sine t minus root 2 sine root 2t. So we could solve part B of the question number 1 as well. Let's go through the part 3. In part 3, we have to solve HD, which is convolution of FT and GT. So we have definition of convolution in the formula sheet. It's given here. So in fact, f star g is equal to the integral from 0 to t ft f tau gt minus tau d tau, and we have Laplace transform of convolution, which is equal to fs times gs. Let's start with definition of convolution. In fact, if you want to find ht is equal to the integral from 0 to t f tau gt minus tau d tau. But we cannot solve this integral easily. That's why it's better to go through Laplace transform of convolution. We know that Laplace transform of ht, it's equal to Laplace transform of ft, which is fs, times Laplace transform of gt, which is equal to gs. Now we can easily find Laplace transform of ft, Laplace transform of gt. Laplace transform of ft based on, so it's going to be equal to fs. Based on definition of Laplace transform, it's integral from 0 to infinity e to the power of minus st times ft dt. So it's equal to, I have to split the integral, so integral from 0 to 1 e to the power of minus st times ft is equal to t dt, plus integral from 1 to 2 e to the power of minus st times ft is equal to 1 dt, and the rest is equal to 0. So you can easily find this integral. The first one you have to use integration by part. The second one is very simple. So you're going to end up with minus e to the power of minus s over s to the power of 2 minus e to the power of minus 2s over s plus 1 over s to the power of 2. Now we have to find Laplace transform of gt. So in fact, gs is equal to the integral from 0 to infinity e to the power of minus st times gt dt, and it's equal to, I have to split the integral from 0 to 1, gt is equal to 1 e to the power of minus st dt. So if you find this integral, you can see that it's equal to minus e to the power of minus s over s plus 1 over s. So Laplace transform of convolution, we know that. So here we said Laplace transform of ht is equal to fs times gs. So I call Laplace transform of ht as h capital S. So in fact, h capital S, which is equal to fs times gs, it's equal to, if I multiply fs by gs, so you're gonna end up with this function. So it's e to the power of minus 2s over s to the power of 3 minus 2 times e to the power of minus s over s to the power of 3 plus 1 over s to the power of 3 plus e to the power of minus 3s over s to the power of 2 minus e to the power of minus 2s divided by s to the power of 2. Now you want to find ht. So ht in fact is Laplace inverse of hs. So ht is equal to Laplace inverse of hs. So it's equal to. So you have to use the second translation theorem. So you're going to end up with 1 over 2 t minus 2 to the power of 2 ut minus 2 minus t minus 1 squared ut minus 1 plus 1/2 t to the power of 2 plus t minus 3 ut minus 3 minus t minus 2 ut minus 2. We could solve part C of question number 1 as well. So we are done with question number 1. Let's go through question number 2. In question number 2, we want to find we have to consider following functions. So fx is equal to 1 minus 2x when x is between 0 to 3, and it's equal to minus 5 when x is between 3 and 4. So we want to find Fourier cosine series of fx, and then we want to sketch the Fourier series on the interval of minus 12 to 12. So in order to solve this problem, so we want to find Fourier cosine series. So if you look at the formula sheet, so we can see that you have the equations for Fourier sine and Fourier cosine here. As a result, you can easily employ them and solve this question. So in part A, we want to find Fourier cosine series. So we know that Fourier cosine series is equal to fx is equal a0 divided by 2 plus summation of an cosine n pi over px. So in this question, x is between 0 and 4. As a result, p is equal to 4. First, we want to find a0. So for finding a0 is equal to 2 over p, the integral from from 0 to p fx dx. So it's equal to p is 4, so 2 over 4 is 1 over 2, the integral from 0 to 4. So the integral from 0 to 4, I have to split the integral because we have piecewise function. So it's from 0 to 3, it's 1 minus 2x dx, and plus half when x is from 3 to 4, we have minus 5 dx. So you can easily find this integral. You're going to end up with a0 equal to minus 11 divided by 2. We could find a0. Now we have to find an. An is equal to 2 over p, the integral from 0 to p fx cosine n pi over px. So it's 1/2. I have to split the integral from 0 to 3. Fx is 1 minus 2x times cosine n pi over pp is 4 x dx, plus 1/2 integral from 3 to 4. So we have fx is minus 5 cosine n pi over 4x dx. For the first integral, you have to use integration by part. For the second one, so it's very easy to find it. So if you use integration by part and you find the second integral, so let's call this integral number 1, and this integral number 2. So if you find integral number 1, you're gonna end up with, so in fact it's equal to minus 20 divided by n pi sine 3n pi over 4 minus 32 over n squared pi squared cosine 3n pi over 4 minus 1. And if you find the second integral, it's equal to 20 over n pi times sine 3 n pi over 4. And if you want to find an, so you have to add them together. So in fact, an, if you add them together, in these two integrals, so I didn't consider half. In fact, I is just, this integral. And here, integral number 2 is just this integral, so I didn't consider half. If you add them together, so you're going to see that an is equal to 1 over 2 times 32 over n squared pi squared times 1 minus cosine 3n pi divided by 4. So as a result, we can say that Fourier cosine is equal to a0 divided by 2. So a0 divided by 2, so we found a0 is equal to minus 11 divided by 2. So as a result, we have minus 11 divided by 4 plus summation of an. Summation of an is equal to 16 over n squared pi squared 1 minus cosine 3n pi divided by 4 times cosine n pi over 4x. So we could find Fourier cosine of the function. In fact, we could solve the first part, but now we have to sketch. You have to sketch the Fourier series. If I want to sketch function using digital pen, so it's not going to be beautiful. That's why I sketched the function on the paper. So now I just bring it here. It's the function, and I explain. Sorry, it's the graph. I explain it here. So in fact, we had fx equal to 1 minus 2x when x is between 0 and 3, and it was minus 5 when x is between 3 and 4. So in order to plot Fourier series, at first we have to just plot Fourier series in this given range. In fact, we have to plot our function. So here you can see that when x is between 0 to 3, so we have function is a linear function is 1 minus 2x, as you can see. And when x is between 3 and 4, so the function is constant and it's equal to minus 5. In fact, we could plot function in the given range, but in the problem, it asked us to just find Fourier cosine. As a result, we have to reflect our function with respect to y-axis. If I reflect it, so we're gonna end up with this plot. Now we have Fourier cosine in the range of minus 4 to 4. What we have to do if you want to have Fourier series in the range of minus 12 to 12, we know that Fourier series is a repetitive function or it's a periodic function. As a result, you have to just plot the same in the range of minus 12 to minus 3, and then you have to plot in the range of 4 to 12. So the final sketch of Fourier cosine would be like what you see in this plot. So it's about part B. Now, sorry, it's about part A. Now in part B, it says that to what values will this series converge at x equal to 0, 4, and minus 12? So you can easily use your plot here. So when x is equal to 0, x is equal to 0, then Fourier series, I call it by g. So g0 is equal to, so you can see that g0 is equal to 1. When x is equal to 4, you want to find Fourier series at 4, so it's g of 4. So you can see that it's this point, so it's equal to minus 5. And if x is equal to minus 12, in fact, g of minus 12, it's equal to, so you can see that here it's equal to minus 5 as well. So we could solve part B of the problem as well. Now we want to go to part C. In part C, it says, without finding the series, sketch the Fourier sine series on separate graph, also on interval minus 12 to 12. So again, if you want to find Fourier sine series, what you have to do, you have to plot your function on the range of 0 to 4. Then you have to reflect it with respect to origin. And now you have a Fourier series in the range of minus 4 to 4. You can easily, you know that the Fourier series is a periodic function. You can repeat it and end up with the final plot. So let's do it here. Again, I sketch this function on the paper and I just bring it here. The Fourier sine series would be in this form. So fx was equal to 1 minus 2x when x is between 0 and 3, and it's minus 5 when x is between 3 and 4. Again, at first I plot 1 minus 2x in the range of 0 to 3, so it's a linear function. You're gonna see that it's this line, and then from 3 to 4 function is constant, is equal to minus 5. As a result, I could plot function in the range of 0 to 3. Now I have to reflect this function with respect to origin. If I reflect this function with respect to origin, I'm gonna end up with this plot. So now I have Fourier series in the range of minus 3 to 4. We have a periodic function. I have to just repeat it from minus 12 to 4 and from 4 to 12. That's it. And I'm gonna end up with this function. So you have to know that Fourier series is a continuous function. As a result, these vertical lines should be plotted as well. So we could solve part 3 of the problem as well. So we are done with question number 2. Let's go through question number 3. In number 3, we want to find Fourier series of the function fx. Fx is a piecewise function, so it's 2 plus x when x is between minus 2 and 0, and it's equal to 2 when x is between 0 and 2. So we want to find Fourier series. It's very simple. So you have the formula in the formula sheet that you have to just apply it and find the Fourier series. So you know that for part A, so fx would be equal to a0 divided by 2 plus summation of an cosine n pi over px plus bn sine n pi over px. First, we have to find a0. a0 based on definition is 1 over p, the integral from minus b to p, fx dx. If you look at the problem, so you can see that the Fourier series, the function is defined on one symmetrical range from minus 2 to 2. As a result, p is equal to 2. So we have 1 over 2 integral from minus 2 to 2 fx dx. And now I have to split the integral, so we have 1/2 integral from minus 2 to 0. So fx here is 2 plus x dx plus 1/2 the integral from 0 to 2 So we have 2 dx. If you find these two integrals, you can easily end up with 3. So we could find a0. Now we have to find an. Based on definition, an is equal to 1 over p, integral from minus p to p, fx cosine n pi over px dx. So I have split the integral, so we have 1/2 here. So we have integral from minus 2 to 0. Fx is 2 plus x cosine n pi over 2 x dx plus integral from 0 to 2. So fx is equal to 2 cosine n pi over 2x dx. So you can easily find the first integral using integration by part. The second integral is very simple. So I just find the final answer. So an would be equal to 2 over n to the power of 2 pi over pi squared. So 1 minus cosine n pi. Now we have to find bn. So bn is equal to 1 over p, the integral from minus p to p, fx sine n pi over px. It's 1/2 integral from, sorry, I have to split the integral. So integral from minus 2 to 0. 2 plus x is fx sine n pi over 2x dx plus the integral from 0 to 2. Fx is equal to 2. So sine n pi over 2x dx. So if you find this integral, so you're going to end up with bn equal to minus 2 over n pi cosine n pi. So as a result, Fourier series of function fx is equal to a0 divided by 2. So it's 3 over 2 plus summation of an cosine n pi over px. So it's going to be an, we already found it. So it's 2 over n squared pi squared 1 minus cosine n pi times cosine n pi over 2x plus summation of bn. Bn is minus 2 over n pi times cosine n pi times sine n pi over 2x. So we have one parenthesis here and one parenthesis here. So we could solve part A of question number 3. So in part B, it says that show the given set of function is orthogonal on the indicated interval, and then find norm of each function and construct one orthonormal set. So the set of function is sine n pi over px. So in fact, we have sine n pi over px, and it's 1, 2, and so on. And you want to show that we want to show that this is orthogonal on the range of 0 to p, and then find normal function. So you know that based on definition of orthogonality, so if you want to have orthogonal set, if you have a set of function like phi n x, if you want to show that it's orthogonal, so you have to show that the inner product of phi n x and phi m x under given range is equal to 0, then n is not equal to m. So for a given set of functions, so sine n pi over px, in fact, you have to show that the integral, or at first, let's go with inner product. I have to show that the inner product of sine n pi over px and sine m pi over px, it's equal to 0. So in fact, the inner product, it's the integral from 0 to p sine n pi over px sine m pi over px dx. So we have to find this integral based on trigonometric equations. So they are given in the formula sheet. It's equal to minus half the integral from 0 to p cosine m plus n over p times pi x plus 1 over half the integral from 0 to p cosine m minus n over p times pi x. You can easily find these two integral if you solve it. So you're going to end up with half minus p over n plus n times pi sine m plus n times pi plus p over m minus n pi sine m minus n times pi. So if you look at here, you have sine m plus n times pi. You know that this guy is equal to 0. And sine m minus n times pi, so it's integer number times pi. So sine of this guy is equal to 0 as well. So we can see that the inner product of sine n pi over px and sine m pi over px on the range of 0 to p is equal to 0. As a result, the function is orthogonal. So we could prove that the set of function is orthogonal. Now we have to find normal function. So you know that normal function, it's equal to root of inner product of sine n pi over px and sine n pi over px. It's equal to root of the integral from 0 to p sine squared n pi over px. Again, so you have to use trigonometric equations. You can see that it's equal to root of half the integral from 0 to p 1 minus cosine 2n pi over px Now you can easily find this integral. So it's equal to root of p and apply upper and lower limit. So you can see that's equal to root p over 2. So it means that we could find normal function. If you want to make one orthonormal function orthonormal set, it's equal to sine n pi over px divided by root p over 2. So this set of function is orthonormal. So in fact, we could solve the third question as well. Let's go through the fourth one. In the fourth question, we want to find steady state temperature distribution on a 7 millimeter by 7 millimeter square aluminum plate by solving the given function. In fact, in this problem, you want to solve one Laplace equation, because you know you have a Laplace equation, second derivative of u with respect to x plus second derivative of u with respect to y is equal to 0, and the boundary conditions, they are given. So u at 0 and y is equal to 0, u at 7 and y is equal to 0, u of x and 0 is equal to 0, and finally u of x and 7 is equal to x times 7 minus x. Let's solve the problem. So in this question, we can use separation of variable because we have homogeneous boundary value problem. As a result, so we can say that u of x and y, it's equal to x of x times y of y. So now we have to find second derivative of u with respect to x, which is x double prime times y, and second derivative of u with respect to y, which is x times y double prime. I have to plug it in the Laplace equation, so we're gonna have x double prime y plus y double prime x equal to 0. As a result, x double prime divided by x, it's equal to minus y double prime divided by y, and it's equal to minus lambda. So we can see that we could end up with two ordinary differential equations. The first one is x double prime plus lambda x equal to 0. And the second one is y double prime minus lambda y, it's equal to 0. So now we have to go through the boundary conditions. So the first boundary condition that we have, it says that u of 0 and y is equal to 0. As a result, x of 0 is equal to 0. Second boundary condition says that u of 7 and y is equal to 0. As a result, x of 7 is equal to 0. And the third one, so we have u of x and 0 is equal to 0. As a result, y of 0 is equal to 0. The fourth one, so we cannot use it right now, it's not homogeneous. So now we have ordinary differential equation, x double prime plus lambda x, it's equal to 0, and we have two boundary conditions. So we have x of 0 is equal to 0, and we have x of 7, it's equal to 0 as well. In order to solve this problem, so we have to consider three cases for lambda. But you know, in the final exam, at the end of second question, it says that for problems number 4 and 5, you do not have to go through all three possible cases for separation constant for lambda. In fact, simply use the appropriate value of this constant in your solution. So you can either check three cases for lambda equal to 0, negative, or positive, or we already solved a question like this, and we ended up, for example, with x double prime plus lambda x equal to 0, subject of x of 0 equal to 0 and x7 equal to 0. And in the past, we saw that for this equation, considering lambda equal to 0 or a negative number, we'll end up with a trivial solution, and we don't need it, so we just need non-trivial solution. As a result, in this problem, I just consider lambda equal to alpha squared. So because I know for alpha squared, I'm going to end up with a non-trivial solution. But in case you are not sure, I highly recommend you to go through all three possible cases and see for which lambda you're going to have non-trivial solution. So if lambda is equal to alpha squared, so we have x double prime plus alpha squared x is equal to 0. Solution of this ordinary differential equation is in the formula sheet. So you can see it's equal to x of x is, let's say I use C1. So x of x is C1 sine alpha x plus C2 cosine alpha x. Now we have x of 0 is equal to 0. As a result, C2 is equal to 0. We have x of 7 is equal to 0. As a result, C1 sine 7 alpha is equal to 0. It means that alpha should be equal to n pi over 7. So we could find x of x. In fact, x of x is equal to C1 sine alpha. Alpha is n pi over 7 times x. Now we have to find y. In fact, we have to solve the second ordinary differential equation that we have here. So we have second ordinary differential equation. So we have y double prime minus lambda y is equal to 0. As a result, y double prime minus alpha squared y is equal to 0. Solution of this ordinary differential equation is in the formula sheet. So y of y is equal to C3 sine hyperbolic alpha y plus C4 cosine hyperbolic alpha y. So we have one boundary condition for y. We found it here. So we said y of 0 is equal to 0. Y of 0 is equal to 0. As a result, C4 should be equal to 0. So it means that y of y is equal to C3 sine hyperbolic alpha y. Alpha, we know that it's n pi over 7. So it times y. So we could find x and we could find y. As a result, we can find u of x and y, which is x of x times y of y. So this solution is valid for all the values of n. As a result, I say it's un of x and y. So x of x, we have it's C1 sine n pi over 7 x. Y of y, we have C3 sine hyperbolic n pi over 7 y. So if you multiply it, you can see that un of x and y, it's equal to, so C1 times C3, I say it's equal to a times an. So we have an sine hyperbolic n pi over 7 y sine n pi over 7x. We could find un of x and y based on superposition principle. So we know that u of x and y, which is summation of un of x and y, is a solution as well. So it can satisfy boundary partial differential equation or Laplace equation and first three boundary conditions. So n from 1 to infinity. So it's equal to summation of an sine hyperbolic n pi over 7y sine n pi over 7x. So the last boundary condition that we have, so says that u of x and 7 is equal to x times 7 minus x. So we have u of x and 7 is equal to x times 7 minus x. U of x and 7, if I plug it in this equation, it's equal to summation of an sine hyperbolic n pi over 7 times 7, so it's going to be n pi sine n pi over 7 x, and it should be equal to x times 7 minus x. So here we have one half range series. As a result, we can say that an times sine hyperbolic n pi it's equal to 2 over 7 integral from 0 to 7 times fx here is x times 7 minus x sine n pi over p, so sine n pi over 7 x dx. So if you have to just find this integral. So this integral you can easily find it using integration by parts. So you're gonna end up with an equal to 196 divided by n to the power of 3 pi to the power of 3 sine hyperbolic n pi times 1 minus cosine n pi. So we could find an as well. So now if you plug it in this equation, so you could find solution of this Laplace equation. So we are done with question number 4. Let's go through question number 5. In question number 5, we have to solve a wave equation. So using separation of variable, the boundary conditions u of 0 and t is equal to 0, u of 1 and t is equal to 0, and initial conditions. So we have u of x and 0 is equal to 3 times sine 3 pi x minus half times half sine 7 pi x, and we have another initial condition, derivative of u with respect to x at t equal to 0, it's equal to 5 times sine 5 pi x. So here the equation that we have is homogeneous. We have homogeneous boundary value problem. As a result, we can use separation of variable. So we say that u of x and t is equal to x of x times t of t. So as a result, if I find the second derivative of u with respect to x, it's equal to x double prime t. Second derivative of u with respect to t, it's x t double prime. Now I can plug it in the equation. So we have x double prime t, it's equal to x times t double prime. As a result, x double prime divided by x, it's equal to t double prime divided by t, and it's equal to minus lambda. We're gonna end up with two ordinary differential equation, x double prime plus lambda x equal to 0, t double prime plus lambda t equal to 0. Now we have to go through the boundary conditions. So we have two boundary conditions. The first one says that u of 0 and t is equal to 0. As a result, x of 0 is equal to 0. The second one says that u of 1 and t is equal to 0. As a result, x of 1 it's equal to 0. And the two initial conditions, we cannot use them right now. So now we have to solve ordinary differential equation, x double prime plus lambda x equal to 0, and we have two boundary conditions, x of 0 is equal to 0 and x of 1 is equal to 0 as well. So again, you have to consider 3 cases for lambda: 0, negative, or positive. But since we solved this question in the past, I know that just lambda equal to a positive number will end up with a non-trivial solution. That's why I just solved this problem for lambda equal to alpha squared. So we assume that lambda is equal to alpha squared. As a result, x double prime plus alpha squared x is equal to 0. It means that x of x is c1 sine alpha x plus c2 cosine alpha x. So x of 0 is equal to 0. It means that c2 is equal to 0. x of 1 is equal to 0. So we have c1 sine alpha equal to 0. As a result, alpha is equal to n pi. So it means that x of x is equal to c1 sine n pi x. Now we have to solve the second ordinary differential equation. The second one is t double prime plus lambda t is equal to 0. So as a result, we have the solution in the formula sheet. T of t is equal to c3 sine alpha t plus c4 cosine alpha t. Now we have x of x, we have t of t, so we can say that u of x and t is equal to x of x times t of t. It's equal to x of x, we have it is c1 sine n pi x times c3 sine alpha t. So in fact, I'm writing t of t, so it's c3 sine alpha t. Alpha is n pi, so it's sine n pi t plus c4 cosine n pi t. So this solution is valid for all the values of n. As a result, un of x and t is equal to c1 times c3, I call it an. It's an sine n pi t. c1 times c4, I call it bn. So plus bn cosine n pi t, all times sine n pi x. So un of x and t is solution based on superposition principle. Summation of un is solution as well. So as a result, u of x and t is equal to summation of an sine n pi t plus bn cosine n pi t, all times sine n pi x. Now we have to find an and bn. For finding an, so we go through the initial conditions. So we have u of x and 0 is equal to 3 sine 3 pi x minus half sine 7 pi x. So we have u of x and 0, it's equal to 3 sine 3 pi x minus half sine 7 pi x. Now I plug 0 in our solution. So u of x and 0, it's equal to summation of an times sine 0, so it's 0. Bn cosine 0 is bn sine n pi x. It's equal to 3 sine 3 pi x minus half sine 7 pi x. So now I can use a half-range series to find Bn, or I can expand the left-hand side of equation. So I expand the left-hand side of equation. So if n is 1, so we have B1 sine px sine pi x plus B2 sine 2 pi x plus B3 sine 3 pi x, and so on. So it should be equal to 3 sine 3 pi x minus half sine 7 pi x. If you compare right hand side and left hand side of equation, here we have sine 3 pi x, here we have B3 sine 3 pi x. As a result, I assume that B3 is equal to 3. So I assume B1 is equal to 0, B2 is equal to 0, B3 is equal to 3. So here we have minus half sine 7 pi x. So I assume that B4 is equal to 0, B5 equal to 0, B6 equal to 0, and B7 is equal to minus half. And other Bn values, they are all equal to 0 as well. So as a result, I can say that Bn is equal to 0, but n is not equal to, when n is not equal to 3 and 7. In fact, when n is equal to 3, so B3 is equal to 3. When n is equal to 7, B7 is equal to minus half. So we could find Bn. Now we have to find An. We have to go through other initial condition. We have derivative of u with respect to x at t equal to 0 is equal to 5 sine 5 pi x. So we have u of x and 0 here. As a result, I can find derivative of u with respect to t. It's equal to summation of, so b as derivative of sine, we have an times n pi times cosine n pi t. Derivative of cosine is minus, so it's minus bn n pi sine n pi t times sine n pi x. So the second initial condition says that derivative of u with respect to t at t equal to 0, it's equal to 5 sine 5 pi x. Now I just plug a 0 in our solution. So we have derivative of u with respect to t at t equal to 0. If I plug t equal to 0 in our solution, cosine 0 is 1. So we have summation of an times n pi minus bn times n pi times sine 0 is 0. So it's gone, times sine n pi x. It should be equal to 5 sine pi x. 5 sine 5 pi x. So again, you can find an using half-range sine series, or you can expand it. So here n from 1 to infinity. If I expand it, so we have a1 n is equal to 1, so times pi so we have, what happened for this guy? We have a1 times pi times sine pi x is for n equal to 1 plus a2 times 2 pi sine 2 pi x plus, and so on. It's equal to 5 sine 5 pi x. Again, if I compare right and left hand side of equation, I have here sine 5 sine pi x. In left hand side, we have a5 times 5 pi sine 5 pi x, so it should be equal to 5. As a result, a5 is equal to 1 over pi. So we could find an, we could find bn. As a result, I can easily find u of x and t. So u of x and t is equal to. So here you have just a5, an is equal to 0 for all the values of n, when n is not equal to 5. So u of x and t is equal to 1 over pi sine 5 pi x, 5 pi t sine 5 pi x plus 3 cosine 3 pi t sine 3 pi x minus half cosine 7 pi t sine 7 pi x. So we are done with the solution of last question, and we could finish the final exam.